Our universe hides more Earths than we ever dreamed. You are about to learn the 24 discoveries that made finding them possible. We will journey from the first shocking detection of a world beyond our solar system to the telescopes now sniffing the air of distant planets. How did a dead star rewrite the rules of where planets could exist? And what strange giant orbited its sun in just 4 days? This story reveals how human ingenuity turned a timeless question into a thrilling scientific hunt. What do you think it will mean for us when we finally find another pale blue dot? For centuries, the search for other worlds existed only in the human mind. Ancient thinkers like Epicurus gazed at the starry void and declared there must be infinite worlds like our own. This radical idea was not without its dangers. Centuries later, the philosopher Giordano Bruno was burned at the stake for, among other heresies, his steadfast belief in a plurality of worlds. His fate underscored a profound truth, that the very notion of other Earths challenged our place in the cosmos. As astronomy matured, the hunt shifted from philosophy to physics. Astronomers who mapped the clockwork motions of our own solar system began to ask a simple, powerful question. If our sun has a family of planets, why should it be alone? This logic fueled a new kind of pursuit. In the mid-20th century, astronomers like Peter van der Kamp believed they had found the first evidence, tiny wobbles in the motion of Barnard's star, suggesting an unseen planetary companion. The scientific community held its breath, only to later discover the signals were false, artifacts of instrumental error. This cycle of hope and disappointment defined the era. Yet each setback only sharpened the tools and refined the methods. It was a necessary rehearsal, a period of immense patience that proved our civilization was not just dreaming of other worlds, but learning how to see them. All that was needed was one definitive discovery to shatter the ancient silence. That silence was finally broken, not around a gentle sun-like star, but in the violent aftermath of a stellar explosion. The first worlds ever confirmed beyond our solar system were found circling a cosmic zombie, a pulsar. This discovery in 1992 was so bizarre it redefined where we thought planets could even exist. Astronomers Alexander Wolskson and Dale Frail were studying a pulsar known as B1257+12, a tiny, ultra-dense stellar corpse spinning hundreds of times every second. It beams out pulses of radio waves with the regularity of a perfect cosmic clock. What they found were tiny, rhythmic changes in the timing of those pulses. The clock was ever so slightly speeding up and slowing down. The only logical explanation was that the pulsar was being gently tugged by the gravity of at least 3 small orbiting worlds. Imagine trying to detect a planet not by its light, but by the way it makes a dead star wobble in its precise rhythm. The planets themselves were nothing like Earth. They were most likely barren, irradiated cinders, survivors of the supernova blast that created their pulsar parent. This was the ultimate proof of planetary resilience. If worlds could form or endure in such an inferno, then they truly must be everywhere. The pulsar planet revolution forced everyone to throw out the old rulebook. Our solar system was not the only template. The galaxy was far stranger and far more fertile than we had ever dared to hope. Just 3 years later, a new discovery shattered the calm. The world of 51 Pegasi b was not merely strange, it was an impossibility. Mitchell Mayer and Didier Queloz pointed their instruments at a sun-like star and found a signature that defied all logic. A gas giant similar in mass to Jupiter was not orbiting at a safe distance. It was clinging to its star in a blistering 4-day embrace. This was a hot Jupiter, a type of world no one had predicted. Every model of how solar systems form said this could not happen. Giant planets built from ice and gas were supposed to form in the cold outer realms, just as our own Jupiter did. How could such a behemoth exist so close to its sun where temperatures would vaporize rock? The answer lay in the method that found it, a technique called radial velocity. Imagine a star with an invisible partner. As the planet orbits, its gravity tugs the star back and forth, causing a subtle wobble. By measuring the slight shift in the color of the star's light as it moves toward us and away from us, astronomers could detect this dance. The wobble of 51 Pegasi was unmistakable. This finding forced a revolutionary idea: planetary migration. Perhaps this giant world formed farther out, then spiraled inward over millions of years, sweeping away any smaller planets in its path. Our own solar system, with its orderly giants, was not the standard model. It was just one possible configuration in a galaxy of endless variety. The hunt was now wide open, and a new method was about to turn a trickle of discoveries into a flood. A new era of exploration began not with a telescope on a mountaintop, but with an observatory launched into the deep silence of space. The Kepler Space Telescope, soaring into the cosmos in 2009, was engineered for a single, monumental purpose. It was built to answer a question that had haunted astronomers for generations: just how common are planets like our own? Kepler's strategy was one of almost unbelievable patience. It fixed its gaze on a single, rich star field, a cosmic cornucopia containing more than 150,000 suns. For years, its sensitive eye did not blink, watching for the telltale signature of a distant world. Its power lay in the transit method. When a planet crosses the face of its star from our point of view, it blocks a tiny fraction of the light. Kepler was so exquisitely sensitive it could detect this minute dimming, a dip in brightness often smaller than that caused by a gnat flying in front of a car's headlight. This technique revealed planets not by their gravitational pull, but by their physical size, casting a shadow across the void. The spacecraft's true revolution was not in any single discovery, but in the sheer weight of numbers. It transformed planetary science from a hunt for individual curiosities into a census of the galaxy. By watching so many stars for so long, it could deliver statistics. It could tell us if solar systems like ours were the rule or the exception, and the data that soon streamed back would reveal a universe far more crowded with worlds than anyone had ever believed possible. Kepler's silent vigil paid off with a thunderous answer. The data, compiled over years of unwavering observation, revealed a staggering truth. Planets do not merely accompany stars, they vastly outnumber them. For every single star you see in the night sky, there is not just one, but a whole family of worlds. Our Milky Way galaxy alone is now thought to host billions, perhaps even trillions of planets. This was not just a new fact, it was a complete overhaul of our cosmic address. We went from living in a sparsely populated neighborhood to residing in a metropolis of worlds. The diversity Kepler uncovered was breathtaking. Some planets complete a full orbit in a matter of hours, skimming so close to their star that their surfaces are likely oceans of molten rock. Others drift in perpetual deep freeze, so far from their suns that a single year might last millennia. Yet amidst this wild menagerie, a clear pattern emerged. The most common type of planet in our galaxy is not a gas giant or a scorched cinder. It is a small, rocky world, similar in size to Earth or the slightly larger super-Earths. The fundamental ingredients for a planet like our own are not rare at all. They are the standard building blocks of cosmic architecture. This confirmed that the process of star formation naturally and routinely spawns planetary systems. Suddenly, the question was no longer if other Earths existed, but where. The hunt now had a specific target, the Goldilocks Zone, that narrow band of space around a star where conditions might be just right for liquid water and perhaps for life. Finding that perfect balance became the new obsession. The idea of the habitable zone, a theoretical band of space where a planet could host liquid water on its surface, gave astronomers a powerful new filter. It is often called the Goldilocks Zone, a place that is not too hot and not too cold, but just right. This zone is not a fixed address. Around a small, cool red dwarf star, the habitable zone is a tight, close-in orbit. Around a massive, brilliant blue star, it is pushed far out into the system. Within our own solar system, we see the stark boundaries of this concept. Venus, shrouded in a thick, suffocating atmosphere, is a scorching greenhouse far too hot. Mars, a barren and frozen desert, lies just outside the outer edge, far too cold. Earth sits perfectly in between. Kepler began sifting through its mountain of data with this new lens, searching for the subtle dimming of stars that signaled a world passing through this precious band. One of its first and most exciting finds was Kepler 22b, a planet orbiting comfortably within the habitable zone of a sun-like star. While this world was far larger than Earth, a super-Earth, its discovery was a monumental proof of concept. It demonstrated that the conditions for liquid water, the one ingredient we know is essential for life, were not unique to our own world. The hunt had fundamentally changed. We were no longer just counting planets. We were starting to grade them to assess their potential. The definition of the habitable zone itself has grown more sophisticated, now considering how a planet's atmosphere or internal heat could expand or contract its boundaries. But this breakthrough gave us our first tangible search image, a way to scan the cosmic ocean for islands of possibility. It was this refined search that would soon lead to an even more profound discovery, the first truly Earth-sized world found circling within that golden ring. The search for a true Earth twin finally had its first tangible candidate. In 2014, the Kepler team unveiled Kepler 186f, a world that checked two of the most critical boxes. It was almost exactly the size of our own planet, and it orbited squarely within its star's habitable zone. Located 500 light-years away, this distant cousin is only about 10% larger than Earth. It circles a red dwarf star, a type of sun that is smaller, cooler, and redder than our own. Because this star emits less heat, the planet must huddle much closer to stay warm, completing an orbit in just about 130 days. Yet at that precise distance, the temperature could theoretically allow for liquid water to pool on its surface. This was the breakthrough that changed everything. Before Kepler 186f, Earth-sized worlds in the Goldilocks Zone were a compelling idea. After its discovery, they were a confirmed reality. Here was a world that was not a bloated gas giant or a scorched super-Earth, but a rocky sphere of familiar proportions, sitting in the sweet spot. It instantly became an icon, a poster child for the possibility of life as we know it. The discovery proved that our planet's basic template, its size and orbital position, is not a cosmic fluke. It is a configuration that the universe repeats. The hunt was no longer for just any habitable zone planet. It was now a focused pursuit for an Earth analog, a world that matches our own in every key aspect. This new goal would demand even greater precision, pushing our telescopes to their absolute limits and forcing us to ask the next inevitable question. If a world like this exists, how could we ever hope to learn what it is actually like? The discovery of Kepler 186f proved Earth-sized worlds could exist in the habitable zone, but it was a single, distant data point. Then came a system that felt like science fiction made real. In 2017, astronomers revealed a cosmic jewel box just 40 light-years from Earth. A small, faint star known as TRAPPIST-1 was not hosting 1 or 2 planets, but a family of 7, each one roughly the size of our own world. This was not merely another exoplanet discovery. It was a paradigm shift. 3 of these 7 siblings orbit squarely within their star's habitable zone, a concentration of potentially life-friendly real estate unlike anything we have ever seen. The entire system is a study in extreme intimacy. All 7 planets circle their star at a distance closer than Mercury's scorching orbit around our Sun. You could fit the whole planetary family well within the orbit of our innermost planet. This compact architecture, discovered by a network of ground-based telescopes and confirmed by the Spitzer Space Telescope, created an astronomer's dream. The planets pass in front of their star very often from our viewpoint, creating frequent, measurable dips in starlight. Their proximity to us means the signal from each transit is relatively strong. This perfect storm of factors made the TRAPPIST-1 system an instant and unparalleled laboratory. For the first time, we were not studying one potentially habitable world in isolation. We were handed a collection of 7, all formed from the same material around the same star, yet each with the potential for a vastly different destiny. One could be a frozen ice ball, another a Venus-like greenhouse, and another a temperate world with liquid water oceans. This system offers a controlled experiment in planetary evolution, a chance to understand why some Earth-sized worlds become living oases and others barren wastelands. The next crucial step was to look beyond their sizes and orbits, to breathe the air of these distant shores by probing their atmospheres. This new question demanded a way to look beyond a world's orbit and size to probe the very air it breathes. The breakthrough came from a technique as elegant as it is powerful, atmospheric spectroscopy. It transformed a distant point of light into a world with an environment we could begin to analyze. The method hinges on a transit, that moment when a planet crosses in front of its star. As this happens, a sliver of starlight does not just bounce off the planet's surface. Instead, it filters right through the planet's atmosphere on its way to us. Think of holding a stained glass window up to the sun. The light passing through it is not just dimmed, it is colored by the pigments in the glass. In the same way, the atmosphere of an alien world imprints its own unique signature onto the starlight. Astronomers capture this faint, filtered light and stretch it out into a spectrum, a rainbow of colors. Embedded within that rainbow are dark lines, the chemical fingerprints of the gases the light has passed through. Each molecule, from simple sodium to complex water vapor, absorbs light at very specific colors, leaving a telltale barcode of its presence. The first successful detections were made around giant, puffy hot Jupiters. Telescopes like Hubble confirmed atmospheres rich with sodium, or the unmistakable spectral signature of water vapor. While these were hostile, sweltering worlds, the discovery was monumental. It proved we could, from trillions of miles away, sniff the air of another planet. This technique, known as transmission spectroscopy, is our most powerful tool in the search for life. It allows us to hunt for biosignatures, combinations of gases that should not coexist for long without a biological source replenishing them. The simultaneous presence of large amounts of oxygen and methane in a planet's air, for example, would be a compelling hint that something is actively, constantly altering that atmosphere. We had graduated from simply finding new worlds to beginning to interrogate them, to ask what it might be like to stand on their surface and look up at their sky. But to push this new science to its limits, to search for these subtle signs in the atmospheres of small, rocky Earths, we would need a telescope of almost unimaginable power. That promise of reading an alien sky required an instrument of almost unimaginable power, and in December 2021 we launched it, the James Webb Space Telescope, unfurling its golden mirrors a million miles from Earth, represented the dawn of a new era. Its mission was to see the unseen, to peer into the infrared portion of the light spectrum where the coolest stars and the molecular signatures of atmospheres shine brightest. With a primary mirror over 6.5 meters across, it collects more than 6 times the light of the Hubble Space Telescope. This colossal power gives it the sensitivity to do what was once pure fantasy, to dissect the thin, fragile atmospheres of small, rocky worlds. Its very design is tailored for the exoplanet revolution, perfect for studying the red dwarf stars where so many of our most promising Earth-sized candidates, like those in the TRAPPIST-1 system, reside. The proof of its staggering capability came swiftly. One of its first targets was a world known as WASP 96b, a scorching gas giant. The telescope did not merely detect an atmosphere, it delivered the most detailed exoplanet spectrum ever captured. The data was a masterpiece of clarity, revealing the unmistakable fingerprint of water vapor and the distinct haze of high-altitude clouds. This was more than a scientific first, it was a declaration. The James Webb Space Telescope had proven it could not only find the air of a distant world, but could begin to read its weather, to parse its composition with a precision that bordered on the miraculous. The tool was now in our hands, calibrated and proven. The next logical step was to point this phenomenal machine at our most cherished targets, the small, rocky worlds orbiting within the habitable zone, and take our first real breath of their air. The James Webb Space Telescope soon turned its incredible precision toward a new atmospheric target, and the result was a landmark achievement. It made the first definitive detection of carbon dioxide in the atmosphere of a distant world, the gas giant WASP 39b. This was far more than just adding another molecule to the list. Carbon dioxide is a fundamental piece of a planet's story. Its presence acts as a key tracer, a clue left over from the planet's formation that tells scientists about the materials that came together to build it. For a giant world like WASP 39b, this discovery illuminates its deep history, but for the search of life, the implications are even more profound. Carbon dioxide is a crucial component in atmospheric chemistry and a major greenhouse gas. On a terrestrial planet like Earth or Mars, it plays a vital role in regulating climate. It helps trap just enough heat from a star to maintain a stable, temperate environment where liquid water can persist. Finding it on a scorching gas giant was not about habitability itself, but about proving we could detect the very type of molecule that makes habitability possible elsewhere. This detection demonstrated Webb's exquisite sensitivity, its ability to pick out the specific chemical signature of carbon dioxide from the faint, filtered starlight of a world over 700 light-years away. It validated the telescope as the premier tool for sniffing out the chemical building blocks of life on distant worlds. With carbon dioxide confirmed, the search for more complex molecules, the ones that might be produced not just by geology but by biology, was suddenly within our reach. For decades, the hunt for other worlds was a study of shadows and wobbles. We knew planets were there by the way they tugged on their stars or dimmed their light. But capturing their actual light, seeing one as a distinct point of glory, was a challenge of an entirely different magnitude. This is the frontier of direct imaging, the quest to take a picture of another world. The difficulty is almost beyond comprehension. A star is billions of times brighter than any orbiting planet. Trying to see that planet next to its star is like trying to spot a single firefly hovering right next to the blinding beam of a lighthouse from miles out at sea. For a long time, it seemed impossible. Then, in 2008, a system called HR 8799 changed everything. Astronomers using the giant Keck and Gemini telescopes captured not one, but 4 worlds, all orbiting the same star. The image was stunning, a family portrait of other solar systems. These were not small, rocky worlds. They were young, colossal gas giants, still glowing with the heat of their formation, and orbiting far out from their parent star in orbits larger than Pluto's. This distance was the key. It provided enough physical separation for advanced instruments called coronagraphs to block the central star's overwhelming glare, allowing the faint, warm light of the planets themselves to be seen. The discovery of HR 8799 proved that direct imaging was not just a dream. It was a viable path to exploring a whole new class of planetary system, one where gas giants roam the outer darkness, much like Jupiter and Saturn do in our own cosmic backyard. The technology to make this happen is as ingenious as the goal itself. Coronagraphs are masks inside a telescope that physically block the light of the star, creating an artificial eclipse. An even more ambitious concept is the Starshade, a giant, flower-shaped spacecraft that would fly tens of thousands of kilometers in front of a space telescope, perfectly positioned to cast a shadow and blot out the star's light, allowing the faint planets to shine through. Why is this direct approach so vital? It allows us to study planets in isolation. Once we have separated a planet's light from its star, we can analyze that light directly, splitting it into a spectrum to understand the composition of its atmosphere, the temperature of its clouds, and perhaps one day, even see the reflected light from its surface. This technique is our only way to study the colder, more distant planets in a system, the ones that transit or radial velocity methods struggle to find. The ultimate goal, the driving force behind every innovation in this field, is to one day capture that first, grainy, monumental image, a single pixel glowing a faint, familiar shade of blue. It would be the picture of another Earth, a pale blue dot not as a concept but as a reality. That single point of light would forever change our place in the universe. Just 4.2 light-years from our solar system, a world of immense promise and profound peril was waiting to be found. In 2016, astronomers announced the discovery of Proxima Centauri b, a planet with a mass at least 1.3 times that of Earth, orbiting squarely within the habitable zone of our very closest stellar neighbor. This was not just another exoplanet. Its location transformed it into something deeply personal, a next-door neighbor in the cosmic sense. Detected by the rhythmic wobble it imparts on its star, this world proved that Earth-mass planets are not just common in the distant galaxy. They are right here in our own celestial backyard. The star it orbits, Proxima Centauri, is a red dwarf, the most numerous and long-lived type of star in the Milky Way. This single discovery meant that the most common stars in our galaxy likely host the most common type of planet we know, small and rocky, and many of them sit in that coveted Goldilocks zone. Yet this potential paradise comes with a terrifying catch. Red dwarfs are notoriously tempestuous. They frequently erupt in colossal flares, blasting their orbiting planets with torrents of ultraviolet and X-ray radiation. For a world like Proxima b, which is likely tidally locked with one side in permanent daylight and the other in endless night, these stellar tantrums could be apocalyptic. They might have long ago scoured the atmosphere away and sterilized the surface, leaving a barren rock bathed in deadly light. Proxima Centauri b thus became the ultimate puzzle, the test case for whether the most common planets around the most common stars can ever be true homes for life. Its tantalizing proximity makes it our greatest hope and our most pressing challenge. It is the only such world close enough that we can realistically dream of sending a probe to visit it, even with technology that lies just beyond our current grasp. This single, faint world forces us to confront the deepest question of all. Is the galaxy quietly teeming with life, or are we living in a universe of beautiful, silent, and sterile islands? Proxima B's discovery forced a difficult truth upon us. A planet's address within the habitable zone is not a guarantee of a welcoming home. The star itself holds a veto power. For the countless worlds orbiting red dwarfs, their parent star's fiery temper can be a death sentence. These small stars are cosmic toddlers prone to tantrums, unleashing monstrous flares that can double their brightness in mere minutes. These eruptions blast out searing ultraviolet and X-ray radiation, enough to strip away a planet's atmosphere and bathe its surface in a sterilizing glow. The very stars that offer the longest-lasting, most stable orbits for life are also the most violently unpredictable. This realization sparked a revolution in our definition of a living world. We began to ask not just where a planet orbits, but how it defends itself. A strong global magnetic field, like the one generated by Earth's churning metallic core, could act as an invisible shield, deflecting the stellar wind and protecting the atmosphere from being slowly eroded into space. A thick atmosphere itself could serve as a buffer, absorbing harmful radiation before it ever reaches the ground. Suddenly, habitability was no longer a simple question of temperature. It became a complex equation balancing stellar fury against planetary fortitude. A world in the Goldilocks Zone might be a scorched and airless rock, while another, slightly colder world with a robust magnetic field and a dense atmosphere could be a sheltered oasis. This breakthrough taught us that a planet's potential for life is a story of relationship, a constant, dynamic struggle between a world and its sun. We learned to look past the orbital diagram and into the heart of a star, understanding that the true cradle of life might be not just a place but a fortress. Kepler revealed a universe teeming with worlds, but its gaze was fixed on a single, distant star field. We needed a new hunter to look closer to home. That hunter was the Transiting Exoplanet Survey Satellite, or TESS, which launched in 2018 with a revolutionary new mandate. Instead of staring deeply at one small piece of the cosmos, TESS would scan almost the entire sky. Its mission was not just to find more planets, but to find the right planets. It focused its gaze on the brightest, closest stars to our solar system, the very stars that are easiest for our most powerful telescopes to study in detail. Think of Kepler as a brilliant demographer, taking a detailed census of a far-off galactic neighborhood. TESS, by contrast, is an elite scout, venturing into our local cosmic territory and planting flags on the most promising worlds for future explorers. Its 4 wide-field cameras act as a panoramic lens, constantly monitoring vast swaths of the sky for the telltale dips in starlight that signal a transiting planet. This strategy has already paid off with thousands of new planet candidates, but the true value of these discoveries lies in their accessibility. When TESS finds a small, rocky world, it is almost always orbiting a star that is bright, stable, and nearby. This is a critical distinction. A dim, distant star offers only a faint whisper of light for analysis, but a bright, close star provides a brilliant, clear signal. It is the difference between trying to read a book in a dark room and reading one in full sunlight. By giving us a curated list of the best and brightest targets, TESS has become the indispensable partner to giants like the James Webb Space Telescope. It points Webb and other observatories toward the specific worlds where atmospheric sniffing has the best chance of success. Every new TESS discovery of a nearby, Earth-sized world is not an end but a beginning. It is an invitation, a cosmic address handed to the next generation of telescopes, saying here, look at this one. Our census of alien worlds had revealed a stunning diversity, but a deeper pattern was hiding in the data. As the numbers climbed into the thousands, a strange gap emerged in the planetary population. It was a cosmic missing link, a mysterious void in the sizes of the most common planets. Astronomers call it the Radius Valley, and it sits between worlds about 1.5 to 2 times the size of our Earth. Planets seem to naturally fall on either side of this divide, leaving the middle ground surprisingly empty. This was not a fluke of observation. It was a fundamental clue to how planets are born and how they die. On one side of the valley are the super-Earths, dense and rocky worlds that are essentially scaled-up versions of our own planet. On the other side are the mini-Neptunes, slightly larger but completely different in nature. These are not rocky giants, but worlds with relatively small solid cores swaddled in immense, puffy atmospheres of hydrogen and helium. They are gaseous with no solid surface to stand on, only endless layers of thick, hot gas deepening into a crushing, fluid abyss. The Radius Valley revealed a critical fork in the road of planetary evolution. Why would a world choose one path over the other? The answer seems to lie in the brutal environment of a young solar system. A planet forming close to its star starts its life by accreting a thick, primordial atmosphere from the gaseous disk. But if the star is too hot and active, that atmosphere is vulnerable. Intense radiation from the youthful star can act like a mighty blowtorch, blasting that lightweight hydrogen envelope away into space, stripping the planet down to its bare, rocky core. What began as a puffy mini-Neptune is transformed into a dense super-Earth. This breakthrough in planetary demographics changed our search strategy completely. It means that not every small planet in the habitable zone is a candidate for life. A world that looks promising from its size and orbit might, in reality, be a gaseous mini-Neptune, a world without a surface, utterly hostile to life as we know it. The Radius Valley gives us a new filter. It helps us separate the true terrestrial cousins, the super-Earths with solid ground and potential oceans, from the gaseous imposters. It tells us that the most common path for a planet is to be either a rock or a gas bag, with very little in between. This understanding sharpens our focus, guiding our most powerful telescopes toward the worlds that are not just the right temperature, but are built from the right stuff. While we were busy staring at individual stars, another spacecraft was quietly assembling a map of the entire galaxy. The European Space Agency's Gaia mission is not a planet hunter in the conventional sense. Its camera is the most powerful ever built for astronomy, and its purpose is pure cosmic cartography. For years, it has been scanning the sky, repeatedly measuring the positions, distances, and motions of over 1 billion stars. The result is a breathtakingly precise three-dimensional atlas of our Milky Way, a living model that shows stars not as static points of light, but as a swirling, dynamic river. This vast census is revolutionizing exoplanet science from an unexpected angle. Gaia detects planets by watching a star's path across the sky. Imagine a single star drifting through the void. If it has an unseen planetary companion, the gravity of that planet will cause the star to trace a tiny, wobbling path as it moves, a barely perceptible stagger in its cosmic stride. This is the astrometric wobble, a side-to-side motion distinct from the back-and-forth tug measured by the radial velocity method. For large planets in wide, slow orbits, this is often the only way to find them. Gaia's staggering precision allows it to detect this stagger, revealing the ghosts of giant worlds by the footprints they leave in the sky. But its true power lies in context. Before Gaia, we knew a planet was there. Now, thanks to this galactic map, we know exactly where there is. Gaia provides the exact distance to a star, which tells us the true brightness of that star, which in turn tells us the true size of any planet orbiting it. A distant, fuzzy measurement becomes a precise, characterized world. This mission weaves every individual exoplanet discovery into the grand tapestry of the galaxy, showing us how these planetary systems are distributed, how they move, and how they fit into the broader story of galactic evolution. It is the ultimate framework, the indispensable background against which the entire drama of other worlds is now playing out. Our search for life was built on a simple blueprint, a planet of rock and air, much like our own. But what if the most promising cradles for life are nothing like Earth at all? Theoretical astronomers have proposed a stunning new possibility, a world they call Hycean. Imagine a planet significantly larger than Earth but smaller than Neptune, a dark world with no land in sight. Its entire surface is a single, globe-spanning ocean, a deep, endless sea. And above this water broods a thick, hydrogen-rich atmosphere, a blanket of primordial gas. These are not the gentle, blue marble worlds we have envisioned. They are steamy, alien water worlds shrouded in perpetual twilight. On the surface, the conditions would be extreme, with crushing pressures and temperatures that could be hot enough to boil water. Yet, within the ocean itself, shielded by miles of water and that dense atmospheric blanket, pockets of stability could exist. The hydrogen atmosphere acts as a powerful greenhouse, trapping heat so effectively that it redefines the very idea of a habitable zone. A Hycean world could orbit far outside the traditional Goldilocks band, receiving very little light from its star, and still maintain a liquid ocean thanks to its own internal heat and its atmospheric cocoon. This single idea shatters the old rules. It means planets we once dismissed as hopelessly inhospitable, like many mini-Neptunes, could in fact be hidden oases. The James Webb Space Telescope is the perfect tool to investigate this radical theory. It can peer into the atmospheres of these candidate worlds, searching not for the familiar signs of oxygen, but for more exotic markers. One such molecule is dimethyl sulfide, a gas that on Earth is produced almost exclusively by marine phytoplankton. Detecting it in the air of a Hycean world would be a thunderous revelation, a strong, indirect hint that life teems in the dark waters below. The discovery of Hycean worlds is not about finding a new planet. It is about discovering a new potential for life itself, forcing us to accept that biology might flourish in the last places we ever thought to look. Yet the most powerful tool in this cosmic hunt might not be a telescope at all, but the remarkable pattern recognition of the human brain. While supercomputers sift through the mountains of data from Kepler and TESS, they can sometimes miss the subtle, strange, or unexpected. This is where a global army of volunteers steps in. Citizen science projects like Planet Hunters have thrown open the doors of discovery to anyone with an internet connection and a curious mind. Ordinary people, from students to retirees, can log on and examine the same light curves that professional astronomers study, looking for the tiny dips that signal a distant world. And time and again, the human eye has proven its worth, spotting anomalies that rigid algorithms overlooked. This crowdsourced approach has yielded spectacular finds, including entire planetary systems that defy conventional models. One of the most stunning was a planet orbiting within a 4-star system, a world with not one but 4 suns in its sky. How could any computer program be trained to expect that? By enlisting hundreds of thousands of volunteers, astronomy has not only accelerated its pace of discovery, it has fundamentally transformed the search into a shared human endeavor. This is more than just efficient data processing. It is a democratization of science, a way for the timeless human wonder about the stars to become active participation. Every time a volunteer marks a curious dip on their screen, they are not just helping scientists, they are joining a grand tradition of exploration, a global community united by the simple, profound question, are we alone? Their collective effort ensures that no strange signal, no matter how faint or bizarre, goes unnoticed in the vast and growing sea of starlight. The search for a definitive sign of life has moved beyond a single, simple marker. For decades, finding oxygen in an alien sky was the ultimate goal, the gold standard for a living world. Our own planet is a testament to that logic, its atmosphere brimming with oxygen pumped out by plants and microbes. But science has a way of complicating our most cherished ideas. We now know that oxygen alone is not a smoking gun. On a lifeless world, processes like the photolysis of water vapor, where a star's intense light breaks apart water molecules high in the atmosphere, can release small amounts of oxygen all on their own. A distant, sterile world could mimic one of our most vital signs of life. This realization forced a profound shift in strategy. The new paradigm is to search not for a single biosignature, but for an entire suite of gases, a chemical chorus that is impossible to sustain without a biological conductor. The most compelling example is the simultaneous presence of oxygen and methane. In a planetary atmosphere, these two gases are natural enemies. They react with each other and destroy one another. To find them both in significant, persistent quantities means something on that world must be constantly, vigorously replenishing them. That something is almost certainly life. The search has also expanded to include more exotic possibilities, gases that would be startling to find anywhere. One such molecule is phosphine, a toxic gas that on Earth is produced by industrial processes or by anaerobic microbes thriving in environments devoid of oxygen. Its recent and still debated detection in the clouds of Venus sent shockwaves through the scientific community, as it is a gas that should be destroyed quickly in the Venusian environment. While not proof of life, it highlights a new willingness to look for the truly strange. This more nuanced approach acknowledges that life elsewhere might not breathe the same air we do. It might thrive in a hydrogen-rich atmosphere or produce gases we have not even thought to look for. By demanding multiple lines of evidence, by looking for chemical imbalances that defy geological explanation, we are building a much more robust filter. We are preparing ourselves not for a simple yes or no, but for the far more complex and wondrous task of interpreting a truly alien biosphere. This flood of starlight data became a new kind of ocean, one too vast for any single human mind to navigate. The Kepler mission alone recorded the brightness of over 150,000 stars for years, generating a dataset of almost unimaginable size. Hidden within that mountain of numbers were the faint whispers of distant worlds, but finding them was like listening for a single, soft voice in a roaring stadium. This is where a new kind of hunter entered the search, one built not of glass and metal, but of silicon and code. Machine learning and artificial intelligence are now the silent, tireless partners in our cosmic quest. These AI systems are not programmed with a simple list of rules. Instead, they are trained, shown millions of examples of what a true planetary transit looks like and what mere stellar noise resembles. Through this process, they learn to recognize the subtle, characteristic dip of a planet passing in front of its star. Their precision is uncanny, able to spot signals so faint and complex that they would have been dismissed as background static just a few years ago. They sift through the noise with a speed and accuracy that dwarfs all previous methods, turning an overwhelming torrent of data into a curated list of high-probability candidates. But their role goes far beyond simple detection. These algorithms can discern hidden patterns in the architecture of entire planetary systems. They can analyze the orbits, sizes, and spacings of known worlds and predict the existence of others we have not yet seen, pointing our telescopes toward the gaps where new planets should be hiding. This is not about replacing the astronomer. It is about creating a powerful new alliance. The machine handles the immense, repetitive labor of scanning the data, freeing the human scientist to do what humans do best: to interpret, to question, and to dream. This partnership is accelerating the entire field, pushing us closer to the ultimate goal: finding that one perfect needle in the galactic haystack, a true Earth twin. Our cosmic neighborhood is not a closed system. In 2017, a sharp-eyed telescope in Hawaii spotted an object hurtling through our solar system on a trajectory that could only mean one thing. It was not from here. Named Oumuamua, this strange, tumbling visitor was the first confirmed interstellar object ever seen. It was soon followed by another, the comet Borisov in 2019. These were not emissaries from alien civilizations, but simple cosmic drifters, likely asteroids or comets flung from their own star systems by gravitational chaos. Their brief passage was a revelation, proving that the building blocks of planets are constantly being exchanged across the vast galactic sea. This discovery ignites an even more profound possibility. If small objects can be ejected, so can entire worlds. Imagine planets torn from their orbits in the turbulent youth of a solar system, cast adrift into the infinite night. These are rogue planets, dark nomads wandering the space between stars. Current estimates suggest there could be billions, even trillions, of these lonely worlds drifting through our galaxy, outnumbering stars by a staggering margin. Finding them is the next great challenge. Their darkness makes them nearly invisible, but a powerful technique called microlensing offers a way. When a rogue planet passes in front of a distant star, its gravity acts as a tiny lens, bending the starlight and causing the background star to briefly and mysteriously brighten. Upcoming missions like the Nancy Grace Roman Space Telescope are being designed to hunt for these fleeting flashes. Catching a rogue planet would be like finding a fossil from another system. Without the overwhelming glare of a host star, we could study its atmosphere directly, analyzing the pristine composition of a world formed around a sun we will never see. These dark wanderers are cosmic time capsules, holding secrets of planetary formation from every corner of the Milky Way, offering a silent, unbiased census of what the galaxy is truly made of. The giants are awakening on mountaintops across the globe. While our eyes in space have reshaped our understanding of the cosmos, a new generation of ground-based observatories is poised to bring alien worlds into a focus once thought impossible. These are the extremely large telescope, the 30-meter telescope, and the giant Magellan telescope, instruments so vast they redefine the very concept of a telescope. Their names are a testament to their scale, with mirrors measuring 39 meters, 30 meters, and 24.5 meters across. To grasp this power, consider that the giant Magellan telescope will collect more light than all of Galileo's telescopes combined, millions of times over. Their primary mission is as audacious as their size: to directly image and analyze the atmospheres of Earth-like planets orbiting our nearest stellar neighbors. The challenge has always been our own atmosphere, the shimmering ocean of air that blurs starlight and turns crisp points into twinkling smudges. This is where a technology called adaptive optics performs miracles. These systems use powerful lasers to create artificial guide stars high in the atmosphere, measuring the distortion in real time, hundreds or even thousands of times per second. A flexible mirror inside the telescope subtly changes its shape, canceling out the atmospheric turbulence. It is like putting on a pair of glasses that instantly correct for the rippling heat haze of a desert road. The result is a view from the ground that rivals, and in some ways may surpass, the clarity of a telescope in space. With this phenomenal resolution, these giants will not just detect the pale blue dot of a nearby Earth, they will be able to spread its light into a spectrum, searching for the biosignatures we have long theorized, the telltale combinations of gases that whisper of a living world. They will watch for seasonal changes in the color of continents, or the glint of sunlight reflected off a distant ocean. This is the promise of the new ground-based revolution, to turn the faintest points of light into worlds we can truly begin to know. These future flagships are not just plans on a drawing board. They are the blueprints for the final stage of this great hunt, missions designed to answer the question that has driven us for centuries. Beyond the James Webb Space Telescope, concepts like LUVOIR and HAB-X are being engineered for a single, staggering feat, to capture the image of another pale blue dot. These would be the largest, most complex observatories ever built, with mirrors dwarfing Hubble's and technologies so advanced they border on science fiction. Their primary instrument is not just a camera, but a starlight suppression system of unimaginable precision. LUVOIR envisions a coronagraph so powerful it can cancel out the glare of a star by a factor of billions, while HAB-X might deploy a starshade, a separate, flower-shaped spacecraft flying tens of thousands of kilometers away to cast a perfect shadow over the telescope. In that manufactured darkness, the faint, steady light of orbiting planets would finally emerge from the stellar glare. We would not just see them as points of light. We would analyze their color, their brightness, and most importantly, their spectra. Imagine pointing such a telescope at a nearby Earth twin and watching for the subtle, seasonal greening of continents, or the telltale glint of sunlight on a liquid water ocean. The spectrum would reveal a chemical story written in light, searching for the simultaneous presence of water vapor, oxygen, ozone, and methane. That particular combination, that atmospheric choir, is the signature we are searching for. Finding it would not just be a discovery, it would be a moment of cosmic contact, the first time we look at a distant world and know, with a high degree of confidence, that we are not alone in the universe. This journey through 24 breakthroughs leaves us with a final, deeply human revelation. The search for other Earths is no longer a niche science, but a force reshaping our very identity. Every new world discovered chips away at the ancient idea of our own cosmic solitude. We now look up at the night sky and know, with certainty, that it is filled with real places, with landscapes and skies of their own. This knowledge radiates outward, touching every corner of our culture. It sparks fierce debates among philosophers and theologians, forcing us to reconsider doctrines of creation and our special place within it. It ignites a primal survival instinct, the understanding that to ensure humanity's long-term future, we cannot keep all our eggs in one fragile planetary basket. This drive propels the once fanciful dream of interstellar travel into a serious engineering challenge, and it imposes a new ethical weight upon our shoulders. If we do find life, even a simple microbe on a distant moon, how will we treat it? Do we have a responsibility to nurture it, or to observe from a distance and leave it untouched? The hunt for a pale blue dot is at its heart a quest for context. It is our species trying to find its reflection in the cosmic dark, seeking to understand what it truly means to be a living world adrift in a sea of silent stars. The greatest breakthrough may not be finding another Earth, but the profound change that the search itself has already wrought within us. Our journey through these 24 breakthroughs reveals a story of relentless curiosity and technological triumph. We began by finding planets in the graveyard of a dead star, a discovery that shattered the old rulebook. We watched as the Kepler telescope transformed a trickle of worlds into a cosmic census, revealing that small, rocky planets are the galaxy's most common architecture. We learned to sniff the air of distant giants with the James Webb Space Telescope, and we are now building the colossal ground-based observatories that will one day turn a pale blue dot from a dream into a picture. Each of these moments systematically dismantled a barrier, pushing back the frontier of the unknown. The cumulative result is a profound shift in our reality. We know now that planets are not rare. We know that Earth-sized worlds orbiting in the habitable zone are not rare. And we know with absolute certainty that we now possess the tools to begin the final interrogation of these distant shores, to search their atmospheres for the chemical whispers of life. This is not the end of the story. It is a thrilling new beginning, a chapter we are writing right now. The next great breakthrough is waiting just beyond the horizon of our current data, perhaps in the form of a disputed spectral line that, upon closer inspection, reveals a gas that should not exist without biology. The hunt continues with more urgency and precision than ever before. Each new observation, each flicker of light from a distant star, brings us closer to answering one of humanity's oldest and most profound questions. Are we a singular miracle, or simply one voice in a vast cosmic chorus? Let us know which of these 24 moments you find most inspiring in the comments below, and subscribe to join us as we stand witness to the next great discovery together.